Welcome back, everybody. We're here talking about describing motion, but we're going to focus on motion graphs today. So this is a little tactics box that you can take a look at. But we're going to start with position versus time graphs. So the most important thing to take away is that the faster an object is moving, the steeper that line will be, assuming it's constant speed. Okay, so that's an important aspect. All right, so repeating that, the steeper the line, the steeper the slope, the faster an object is going. So this bold right here, that is important. We of course calculate the slope, the steepness of a line by doing rise over run. It's the change in the y value divided by the change in the x value. In this case, position versus time graph, it is a change in displacement, or change in position, you could say, divided by the change in time. All right, and that slope, when we find it, the value of that slope is equal to velocity. All right. And it says here at this point in the motion, right? Well, if you have a constant motion, the slope is going to be the same over that whole interval. So this is the graph that we looked at from a similar previous slide. The oops, you get the idea. The motion during this section A is going to be the same, the velocity is going to be the same from 0 to 3 seconds. And then from 3 to 6 seconds in section B, the velocity will be the same no matter where you find that slope. If you take it at a point or a series of points, it doesn't matter. From a position versus time graph, you can determine the velocity versus time graph very simply. So in these three sections of motion that we talked about just on the previous slide, we have A, we have B, oh, there's that dreaded line again, and then C. Each of those has a constant slope. So over those time intervals, you find the slope, you take a value, and then you write that on the graph here. Now this is a little strange. I don't know why they did this. In the position versus time graph, they have position versus time in minutes, but then in velocity, they have velocity in meters per second versus minutes, which is a little strange to do that. Usually we stay consistent and have all the units the same, meaning time units all would be seconds. So if you're wondering why the slope of 200 over 3 is 1 meter per second, that's the reason. All right, here's a motion diagram. We have some two sections of constant motion. So we have this first section here of these three vectors. If it's a certain time interval, they're moving the same speed over each three time intervals. And then for this next section, it is moving faster over the whole thing. Notice that the number line is kind of underlaid here. So this is our 0 point. So it starts to the left of the number line, which for velocity graph may not, or does not matter, I should say, because it just tells you which direction it's moving. It's moving in the positive direction the whole time, so that means we're going to have positive velocity the entire time. So which graph, A, B, C, or D, can represent this motion? So it starts off moving slower, and then it increases. So, of course, it would be C. So remember, during the time interval, the first time interval with those three arrows, the velocity is not changing. It's remaining constant, which is why this section here is flat. It's a constant velocity. In A, B, and D, I guess not D because it's 0, but in A and B, the velocity is changing in each of the first sections. And same thing with the second. This is a constant velocity. The only difference is that it's a higher constant velocity. And in both A and B and D, the velocity is increasing, which this does not show. Now there's a car moving to the left. All right, same idea. Constant velocity in the first section, larger constant velocity in the second section over here. But it's heading towards the origin. All right, it's heading towards the origin. So what does that look like? Well, is this positive velocity or negative velocity? That's the first thing we should ask. And it is negative velocity because it's moving to the left. All right, so which graph could match this motion? Well, it has to be negative velocity. And when we look at that, you would say that D is the correct answer. Let me move this down so you can actually, there we go. There, much better. All right, so you can see now D. So it starts off moving at a slower speed. So we have this closer to zero velocity, and then it increases, and you have a higher speed for the second time interval. Now the strange part about this, I would say, just looking at it, is the fact that in order for this graph to be the correct one, you're kind of looking at this from right to left. So it's a little strange, right? Because a lot of times we read things left to right, but the car starts on the right-hand side and goes to the left. So the time would start from where it begins and then go from there. Okay. Here's another one. All right, basketball player moving down the court appears as follows. So this is a position time graph. Now we're going to go from position to velocity. All right, so you take the position, the slope of the position time graph, and transfer that to the velocity. So very simply, the slope of this beginning part is 0. It's a flat section right here. So that is a slope of 0. So that means the velocity has to be 0. So that rules out A right away. Can't be A. And then what do we know about this slope? Well, it's a negative slope, right? And it's a constant value. So that means the velocity is not changing. So it can't be B because the velocity is changing in B. Now then the question is, all right, is it C or D? Well, we just said it's a negative slope, and therefore you have a negative value. So you can't have a positive value. It can't be that. It's got to be C. Okay. All right, position time graph of a car. So it says draw the car's velocity versus time graph and describe the car's motion. All right, so let's see. If we think about this, the object on a number line, what direction does the car start moving? Well, if we use a standard setup here, and we say 0's in the middle, right? This is positive and that's negative, right? So to the right is positive, to the left is negative. What direction does it start moving? Well, it starts negative displacement. So it starts moving this way. So it starts at 0 and it heads to the left. And it moves at a certain speed, a constant speed, until 2 seconds, and then it stops. And then it stops for, 3 seconds. And then it turns around and it goes back. And in fact, it starts from here and goes back and goes quite a ways back to the other side until it hits 6 meters, or actually more than 6 meters away from the origin. All right. So you can read this part, but use the slopes, right? Section, if we call this A, and then this B, and this whole thing, I'm going to label as C because the slope is constant, and therefore the velocity is constant. A has a negative slope, so that means it's moving in the negative direction, but it's moving at a constant speed in the negative direction. B, no slope, 0. So it's not moving, it stops. And then it turns around and moves at a constant speed in the other direction. And that's what we see here. All right, so this kind of runs through. You can look at this. You calculate the values. So we start off with a value of -2 meters per second. And then for 3 seconds, there was a value of 0 meters per second because that is the slope. And then the final slope, that positive value, is 5 meters per second for the last 2 or 3 seconds there. All right, so this runs you through. Let's see. This is just some more information. So take a look at this, pause this, you can read it. All right, velocity to position. Now, going backwards can be a little challenging, but once you understand what you're looking for, then you're okay. So you can, it says you can deduce the position versus time graph from a velocity, and the reason sometimes there's one piece of information that you do not know, and that is the starting position. All right, you can assume that the starting position is 0, but we do not know that. So if any problem doesn't tell you if you're going from velocity versus time to position versus time, unless they tell you the starting position, you don't know it. So you can assume that it's 0 just to make it easy. But that is what we're looking at here. The sign of the velocity. So if you have positive velocity, that means on your displacement versus time graph, the slope of the line is going to have a positive value. Because remember, that's how we go from position to, or displacement to velocity. So in this case, up top, we have the positive value of 1 meter per second. So we know that the line down here has to have a slope of 1 when we take rise over run, okay? So that has to have a slope of 1, positive 1 in fact. All right, down here, -3, so this is going to have a steeper slope. When we calculate this slope, or we do rise over run here, that value has to end up with being a -3. Right, so you can absolutely go from one to the other, position to velocity, velocity to position. All right, here's a car moving in a straight line on a road. It's the same motion diagram we've looked at, right? Which position versus time graph matches this? Let me think. Take a second. Try. I think I've been blocking these, so I'm going to try to move myself up there. All right. Which one of these? So it's moving to the right at a slow speed, but it starts to the left of 0. That's important. So it doesn't start at 0. So what does that mean? That means that A is out. And it means that D's out. Okay. Starts to the left. All these three, B, C, and E, all start to the left. So if you go through, it starts off slow, and then it gets faster. That's E is the only one that shows that. Velocity versus time, hockey puck shot into a goal. This is velocity. So first section has to have a positive slope. Second section, a slope of 0. And of course, that would end up with D. All right, this is a little tricky. Now, this gets us into a changing velocity, because we said that you find velocity from a position graph by taking the slope. Well, what happens if the slope is changing? So if we can measure that change in the slope, we can tell what the object is doing. All right, so if we have a steep slope, object is moving fast, whether it's in one direction or another direction. Could be positive slope, negative. If that slope begins to flatten out in any way, that object is slowing down. If that slope gets steeper, then it's speeding up. So right here in this, we see an object moving kind of fast, and then the slope getting flatter, which means that it's slowing. So if it's slowing down, now we know that the velocity has to be heading towards 0. So it's either C or D. And we have C up here, right? Because the slope is positive the entire time.